key takeaway is that you have a class, which I guess is a group of operations, right? And you
Yeah,
can,
every class is operations that in your heart, you know the equivalent.
if
You
you
either do
apply the
this or
appropriate
you run around, totally different operations. They form classes.
if you apply the appropriate character table to the class, right? The classes, you will get the natural coordinates out of that.
Yeah,
Okay.
our game is always to go to intrinsically correct coordinates.
Okay.
I'm doing my measurement in my own coordinates because, I'm human, but there is an intrinsically correct set that's eigenvalues and eigenvectors of the operator.
Mhm. And then I had two questions from before. One is you if you add reflection to rotation, is it analogous at all to permuting particles and making them, instead of distinguishable particles, indistinguishable? Reduces the number of permutations.
I think of them as indistinguishable physically, but labeled. I don't know
Okay.
whether that helps.
Hmm.
So the n factorials in statistical mechanics and quantum mechanics show up because of that, because you have some number of particles. There are 3 electrons. So when you write your equations, they're called electron 1, electron 2, and electron 3, and they're moving around doing their things.
Hmm.
But because they're indistinguishable physically, you have to divide your results by 1 over 3 factorial because you're overcounting what's going on.
Hmm.
So, so they're labeled but indistinguishable always.
Okay. And then the other thing you mentioned, that you said like maybe the most A1, right? The most symmetric combination you can have is if you sum all of the operations and you average over the
Yeah.
size of the group. So I was just wondering, how is that the case? Because I know if you do like calculate the expectation value of an operator on a state, you get an average. It's not necessarily an eigenvalue of the.
No, it's not an eigenvalue. Average is not an eigenvalue. No.
So how do you know that it's in fact actually symmetric or part of the group?
Well, in this, we're staying all the time within linear algebra, in which case it's quite simple, right? In linear, this is obviously symmetric. I
Okay,
take,
okay. Yeah, if
I
you add
take.
symmetric matrices, right? Or wait.
Well, no, the matrices are not symmetric, but I take my function. So that's why I went very slowly through the case of reflection of 2 group elements. If I take my function and flip the axis and add the 2 things, that's obviously symmetric because under all group elements, it doesn't change, right? If I flip a symmetric function, it's the same function, right?
Yeah.
And then when you do it on a propeller, if you rotate it by 1/3, it's the same function because it's a sum of all 3 things. So as you rotate it, they just get permuted as elements of a sum, but sum is invariant.
Okay, so all of these operations that we are summing to get this result, all they all leave the system invariant.
Every irreducible representation is invariant representation under symmetries.
Okay. Okay.
Because, why is that? Because of rearrangement theorem. So what happens is that every sum that we look at is a weighted sum of the group elements, weighted by characters.
Mm-hmm. Okay.
So, for symmetric, it's always 1. For antisymmetric, half of them are -1. And then for any other case, there's some Cupid numbers, phases, etc. But because of rearrangement theory, when I apply any group operation to this sum, it just rearranges the elements. So, for example, rearrangement theory within a class. It just rearranges guys within the class, but doesn't change the class. There is no, in the caste society that we are, there is no group operation from which I could, go from bouncing between two balls to running among three. It's not an option.
Okay.
So the classes are invariant concept. The most that can happen is members can be relabeled, permuted, but the class, some of them doesn't change.
I actually was asking about when you write like phi of A1, phi sub A1 equals 1 over n sum of identity plus sigma 1 plus sigma 2 plus sigma 3 plus G squared. So those three groups, like identity,
Three
sigma 1 plus sigma 2,
three classes.
three classes.
What's kind of confusing, you have subgroups, you have classes, you have cosets. Totally crucial, you distinguish a subgroup from a class. So these are classes.
Okay, so the class is a sum, sigma 1 plus sigma 2 plus sigma 3.
That's a class. Yeah.
The sum of all those three.
It's a sum of three.
The sum, okay. Though all the classes equal identity.
No.
No? Okay. Because I was just thinking G plus G squared, or G plus G2. That would be like rotating 1/3 and then 2/3. That gives you identity. I was wondering if...
Yeah, but that's, that's a special case.
Okay. So it's not identity. Okay.
They're not identity because there'll be no group theory. If every class is identity, there's nothing to do. We go home.
Okay.
The whole point is that they're different.
Okay.